So some definitions to start off with. What is probability? Well, simply the chance of something happening. We call that the probability. Now, experimental probability, also known as relative frequency, is when the probability is actually based upon some experiment, some data that we've collected, rather than the theoretical probability. So if we toss 5 coins and they happen to land head, head, tail, tail, then head, we'd say the experimental probability of tossing a head would be 3/5. Now we know in reality, of course, it's 1/2. But by just looking at the experiment, we would assume that it's 3/5. So that's the difference between experimental probability and our theoretical probability. Now, what should happen? The more times you repeat an event, the closer and closer your probability, your experimental probability, should be to the theoretical probability. So if it was possible to toss that coin an infinite number of times, then we would expect to see half of them being heads and half of them being tails. And so the more times we do it, the closer it becomes. Sample space, well, that's all the possible outcomes that we could have. That's what we call our sample space. And event space is the number of different ways the particular outcome we're interested in could happen. Equally likely events, well, they're just things that have the same probability of happening. So a head and a tail, they're equally likely. Geez, we come up with some good names, don't we? Mutually exclusive events. So mutually exclusive means that these outcomes are independent of each other. Only one possible outcome could occur at any one time. We could say a coin, it could be a head or a tail. It can't be both. So the event of head and the event of tail are mutually exclusive. Which then brings us to non-mutually exclusive events, and that's when more than one outcome could happen at the same time. For instance, I might be choosing numbers or rolling a dice and looking at the numbers. It is possible to have 2 different events. One of those might be that it's an even number, and the other might be that it's a multiple of 3. So it is possible that both events could happen at once. So that would be a non-mutually exclusive events. Some notation. P with whatever the event we're looking at or considering, that simply means the probability of the event happening. Don't just write numbers down. Okay, this is again where I guess senior maths is a bit different to junior maths. The setting out, we're more interested in, let's set it out so that if someone's reading my solution, they can understand what we're saying. So if I wanted the probability of a head, I wouldn't just write down half. Because someone's reading it, all they're seeing is the number of a half. There's no context to it. So you would say, oh, probability of a head equals a half. There's no context to what this half means. And the complementary events, if I put a bar over the top of E, would be the probability of E not happening. So I'd say it's called the complementary event. Bit of probability theory then. That, I guess, is the key to everything. Probability always falls between 0 and 1. And theoretically it could equal 0 and it could equal 1. But it's never going to be negative, and it's never going to be bigger than 1. If it does happen to equal 0, then we would say that event is impossible. There's no probability. It could not happen at all. Over at the other end of the scale, probability equals 1 is a certain event. It must happen. There's no other thing that could happen. E must happen. And so then, if our events are equally likely, of course, then the sample space would be uniform. So it'd be a nice even scale, if you like. And there's a formula, not that we usually use a formula, but there's a theoretical formula for how you work out probability. The probability of E is equal to what at the moment looks like absolute value of E over absolute value of S. What does it mean? Well, absolute value of E represents in probability the number of times E would occur, or the size of the event space. And absolute value of S, that's the total number of possibilities, or the size of the sample space. Now, a lot of times you just do that intuitively anyway. You don't write the formula down. But as I say, theoretically, that's your formula for working out probability. The complementary event then, because they've all got to add up to be 1, so the probability of something not happening must be 1 minus the probability of it happening. And that can be useful because sometimes it's easier to work out the probability of something not happening rather than trying to work out the probability of it happening. So some ideas of how we can work out all the outcomes. How do we list our sample spaces? Certainly important in what we call multi-stage experiments, more than one event. We could simply create a list. We could just simply write down every possibility that there is. Here's an HSC question. In a game, a turn involves rolling 2 dice, each with faces. It's unusual dice. It's not going from 1 to 6. It's going from 0 to 5. The score for each turn is calculated by multiplying the 2 numbers uppermost on the dice. So, all right, start this problem by simply, let's write out every possibility. So I gave 0 times 0, 1 times 0, and so on. So there's 36 possibilities there. Some of them are the same as others. And so the first part of this HSC question was, what's the probability of scoring 0 on the first go? Well, there they all are. They go down that column and across that row, and I can just simply count and go, oh, look how many there are. So there's 11 out of the 36 possibilities. That's probably the simplest way of solving part 2. What is the probability of scoring 16 or more? So again, I turn to my sample space, 16 or more. There we go. There's 4 of them. So 4 over 36, which is, of course, 1 over 9. Second idea, dot diagrams. Okay, this is certainly useful when it's a 2-stage. So here's a question. We're going to roll a pair of dice. This time they're just regular ones, going from 1 to 6. What's the probability, first of all, that they total 3, and second of all, total 7? So the sample space, very similar to what we just saw, but instead of writing 1, 1, 1, 2, and so on, I've drawn up a grid where 1 to 6 down one side, 1 to 6 down the bottom, and I put a dot for every possible outcome. And in this case, all of those outcomes are possible, so I have 36 dots there, rather than physically writing each individual one down. So all right, probability that they total 3, just like the last question, it's a matter of just looking at our dot diagram now. Okay, 2 plus 1 would give me 3. There's 2 possible ways of doing it, 1 in 18. Total 7, okay, we could have 1 in 6, 2 in 5, and so on and so on. 6 out of 36, so 1 in 6. In fact, that is the most common outcome for rolling 2 dice, which explains why, if ever you look at a dice, the opposite sides of a dice add up to 7. What's the probability of totaling at least 3? Now, at least 3. Gosh, I've got to work out 3, 4, 5, 6, 7. This is where the complementary idea is going to work out, because rather than working out 3, 4, 5, 6, 7, 8, 9, I could work out the opposite, or the complement, which would be like just 1 or 2. And I've only got 2 things to work out. So if I go 1 minus that, and there's 1, the only way we can get it, well, we can't get 1, can we? Not with 2 dice. So there's only one possibility, a 1 and a 1. So it's 1 minus 1 on 36, 35 on 36. And probably the most common way that you would have seen is drawing up a tree diagram. This is especially useful when the outcomes are not equally likely. So notice that the dot diagram was good because they were equally likely, so I could simply count, and I knew the probabilities were going to be the same. Tree diagram helps me if they're not. So what have I got? We've got a raffle, 30 tickets are being sold, 2 prizes all up. Probability, someone buys 5 tickets, but they end up winning exactly 1 prize. So we'll branch out. They draw the ticket for the first prize. I could either win or I could lose. But the probabilities are not equally likely. So I will write the probabilities on the branch of the tree diagram. And we had bought 5 tickets out of the 30, so I have a 5 in 30 chance of winning, 25 in 30 chance of losing. but they're going to draw a second ticket. Now, depending on what happened in the first time, it's going to affect the probability of the second time. So if I did happen to win, then one of my tickets has been pulled out. There's 29 left. So the probability of now winning the second prize as well, 4 out of 29 and 25 out of 29 for not winning. However, had I have lost the first go, now the chance of winning is 5 in 29 and losing is 24. So there's all my outcomes. I could have gone win and a win, a win and a loss and a win, a loss and a loss. We're interested in which one of those. What's the probability? Exactly one prize. So that would be win and a loss and a win. So I want those two. And there's the probabilities of all the outcomes. So win and a loss and a win ends up being 25 on 87. 25 on 87. What's the probability of winning at least one prize? That word at least, that's usually a bit of a hint of use the complementary event. It's sort of a, hey, I might look at that. Because it is going to be easier to work out the complementary event, which is, of course, winning no prizes at all. So 1 minus the probability of no prizes is 9 on 29. Chances are, we'll work on these. Chances are, see what I did there? Oh, yeah. Good, wasn't it?